Hello everyone, my name is Fatemeh Soltan and I hold a master's degree in astronomy and astrophysics. I'd like to thank the Cosmology from Home organizers for this opportunity. Today, I'll present my master's research on multi-field mimetic gravity, a modified gravity theory that extends the original mimetic gravity model proposed by Shamseddin and Mukhanov in 2013 to address the dark matter problem. Let's dive in. In this presentation, I will introduce the mimetic gravity model and its instabilities, discuss the extended multi-field model, analyze the cosmological dynamics using dynamical systems to explore the behavior of the model, and compare the results with the lambda CDM model and summarize the key conclusions of my research. Mimetic gravity is a reformulation of general relativity that extracts the conformal degree of freedom. It uses an auxiliary metric and a scalar field to redefine the physical metric, leading to modified field equations. The term arising from the scalar field behaves like a pressureless perfect fluid, effectively mimicking cold dark matter in an FRW background. The mimetic constraint, which ensures this behavior, is imposed via a Lagrange multiplier. The mimetic gravity model lacks a dynamical mode, despite perturbation level stability. Higher derivative terms can induce dynamics but may cause ghost or gradient instabilities. There are two potential solutions: coupling with the spacetime curvature tensor and introducing multiple scalar fields. These strategies aim for a stable dynamical mimetic gravity model. The multi-field mimetic model proposed by Mansouri et al. In 2022 constructs the physical metric using an auxiliary metric and several scalar fields. It ensures conformal invariance under transformations of the auxiliary metric. The scalar fields evolve within a curved field space with metric GAB of phi c. A generalized mimetic constraint is applied in the action through a Lagrange multiplier lambda. We begin our cosmological analysis by deriving the background equations of motion. The mimetic constraint comes from varying the action with respect to lambda, and taking the covariant derivative gives another key relation. We derive the field equations by varying the action with respect to the metric and scalar fields. Assuming a perfect fluid and conserved matter, we obtain a closed system of dynamically linked equations. To analyze the phase space, we consider two scalar fields, phi and psi, and study two potential types, interacting and non-interacting. We assume constant field space metric and first derivatives during evolution. The dynamical systems approach uses dimensionless variables to rewrite cosmological equations as first-order autonomous systems. Critical points represent fixed solutions and are classified based on the sign of their eigenvalues. This analysis enables an understanding of the evolution that is independent of initial conditions. First, we explore the interacting potentials case. We introduce dimensionless variables, also consider these parameters. Using these variables, we express the energy density and effective equation of state parameters. By differentiating with respect to ln of A, we obtain the autonomous system. Setting derivatives to 0 gives us critical points. We linearize around each point and analyze eigenvalues to assess stability. Table 1 presents the critical points and their cosmological interpretations, and Table 2 provides eigenvalues and stability conditions. This model yields various solutions. A1 and A2 matter-dominated solutions, standard model behavior. A6 dark energy evolution. A6 dark energy domination with omega EFF equals -1, mimicking a cosmological constant. A3, 4, and 5 scaling solutions with omega EFF equals omega, so no acceleration with standard matter. A7, A8, and A9 also scaling, but can show acceleration for specific parameters and may describe the universe's late time behavior. In summary, regardless of the scalar potential form, the system always admits matter-dominated, dark energy-dominated, and scaling solutions. Scaling solutions are crucial for addressing the coincidence problem. The next step is to analyze these solutions for specific potentials. Numerical analysis with an inverse square interacting potential yields phase space diagrams for two omega values. Diagram A, expanding solutions evolve from matter domination towards the accelerating attractor A9 plus, aligning with observations. Constructing solutions approach attractor A9 minus. Diagram B, the universe transitions from radiation domination A1 to matter domination A2 and finally to the scaling solution A9 plus, matching the correct thermal history. The stabilization of dark matter and dark energy densities near 0.3 and 0.7 respectively demonstrates late time acceleration, addressing the coincidence problem. Analysis with a power law interacting potential shows the universe evolving from matter domination to dark energy domination. It approaches the center point A6 plus, a saddle point, and stays near it temporarily. Phase space diagrams depict the trajectory moving from the critical line A1 toward A6 plus. Though no finite attractor exists, an attractor at infinity emerges. For non-interacting potentials, we follow the same process. Define dimensionless variables, um, parameters, and density parameters, and effective EOS parameters. And form a dynamical system, then analyze critical points and curves. Matter and Matter and mimetic dominated phases A1 and A2 are unstable, allowing for cosmic evolution. Scaling points A3, 4, and 5 enable intermediate epochs as saddle type solutions. The sitter-like solutions A6, 7, and 8 indicate accelerated expansion. Points A9 and A10 can be stable and accelerating, uh, making them potential candidates for modeling the current universe. In summary, the model accounts for matter domination and a late time acceleration without relying on specific potential forms. For an inverse square non-interacting potential, figures with omega equals 0, the x-axis separates expanding and contracting universes. Expanding ones aligned with observations, transitioning from matter domination to accelerated scaling solutions A9 and A10. And omega equals 1/3 shows a cosmic evolution from radiation domination A1 to matter domination A2, and finally to accelerated expansion A9 plus and A10 plus. Both cases address the coincidence problem with dark matter and dark energy densities stabilizing around 0.3 and 0.7 respectively. Numerical analysis with a power law non-interacting potentials yields an energy density evolution plot that confirms the absence of a final attractor in a bounded region. Two phase space diagrams with specific variables set to 0. A6, 7, and 8 exhibit saddle behavior, indicating dark energy dominated phases. However, no stable accelerating attractor exists within a finite region. An attractor only emerges at infinity. The lambda CDM model describes the cosmic epoch sequence, radiation, matter, and dark energy domination. Our multi-field mimetic model, particularly with the inverse square potential, successfully reproduces this sequence. However, unlike lambda CDM, it naturally admits scaling solutions and offers possible resolutions to fine-tuning and coincidence problems. It not only reproduces the correct cosmic history, but also offers key advantages. Scaling solutions align with cosmic epochs, potential resolution of the coincidence problem, no need for fine tuning, and despite lambda CDM's observational success, our model could better explain cosmic evolution dynamics. Thanks for your attention.